Thank you, and thank you for inviting me to this conference. Okay, so it's a pleasure to be here. Really enjoyed my 2 days in St. Andrews. So the talk today is about distributed consensus. It's a rather old problem, and we have been working on it for the last many years. Before I start, acknowledgments to my collaborators, several students and several faculty colleagues, and the funding agencies. Actually, I'm not going to go into details of any of our results today at all. I realize the audience is very broad. So the outline is really just an introduction to the problem itself. And some of you may have taken a class on distributed systems and should know these things already. And then I'll list 3 or 4 open problems. Of course, there are problems that we have worked on and haven't solved them fully yet. And that will be at the end of my talk. I do have a lot of slides. That's just what I do. But do ask questions during the talk if you have. And I'll stop at 3:30. I'll promise that. So let's begin. So consensus, the dictionary definition, of course, is that there is a general agreement. And the technical definition of consensus is not that different from the dictionary definition. I'll make it a little bit more precise than this. But this particular problem has received enormous amount of attention in the last 30 to 40 years, largely from 2 very different communities. One is distributed computing, to which I belong, and then there's another group that is not represented today here in this room, decentralized control. And they're coming at the same problem from 2 different perspectives, different motivations. So I'll give a very brief summary of the 2 perspectives and summarize the key results in the 2 areas, and then define these open problems that I promised to discuss. So first, distributed computing, which some of you here must belong to that area. So this is the definition of consensus. And there are many variations on this basic theme. But the idea is that there are multiple agents or many nodes in this system. And each node has an input of some sort. And at the end of the day, all the agents, all the nodes produce an output. Each of them has an output. And those outputs have to satisfy these properties. So if all of us are executing consensus, then we should all have the same output at the end of the algorithm. The output has to be valid. We cannot produce, for example, a default output in every execution. The output must be somehow related to the inputs. And the validity, one of the common conditions is stated this way. The output has to be in the convex cell of the inputs at the different agents or different nodes. And then, of course, we must terminate eventually. We don't want the algorithm to run forever without producing an outcome. So these are the 3 conditions that are classically defined for the consensus problem: agreement, validity, and termination. So here is an example. Suppose you have 3 agents, and they have inputs 1, 4, and 6. So the output has to be some function of the inputs. It should be in the convex cell, which is just the range 1 to 6 for the scalars. Now, depending on which version of the problem you look at, perhaps the output can be any number in this range. So it could be 3.5, 3.49, whatever you want in that range. Or you may require that the output should be equal to one of the inputs. So output has to be either 1, 4, or 6. Output has to be discrete. So different flavors have been looked at in different contexts. If you have vector inputs, then the picture is similar, except that the convex cell in this case is now a triangle because you have 3 points in 2 dimensions. But the dimension could be larger than that. So the common example where, in practice, consensus is used today is in this context. If you have data that is stored on many, many different servers, right? There could be servers that are spread across the globe, and you want to keep these servers or the state of the servers consistent. So you're doing some sort of replicated state machine, and the way to maintain the state consistent is for the servers to execute the same commands in the same order, so they must agree on the ordering of the commands that they're executing. And that's likely the most sort of common example in practice where consensus gets used. So instead of that, let's take a simpler example that many of you probably had to do. May have had to solve this problem a couple of nights ago when you arrived here. So let's say there are 3 of us who want to go out for dinner tonight, and 3 of us have different choices for where you want to go. I did not tailor my slides to St. Andrews. I don't know if there's a Korean restaurant at all, but let's say there is. And so 2 of us propose Korean, and 3rd proposes Thai. And of course, we want to agree on one place to go to. You don't want to end up in different places. So how are we going to solve this problem? The solution is sort of obvious. We do this routinely. Achieving consensus will require some communication between the parties. And the simplest solution is for each of us to broadcast our preference to everybody else, right? So each of us sends our preference to other people by email. And when you execute that round of communication, then all of us get 3 preferences. Here, K stands for Korean and T for Thai. So I learned 3 preferences from 3 of us, and so on. And if all goes well, we all learn the same 3 preferences. And then you can choose one decision, the one output, as some deterministic function of these 3 values. So perhaps you pick the majority, and then the outcome is k. So this is sort of the routinely how you might solve the problem in practice. The trouble is that the distributed systems that we deal with are not this benign. There are issues that you need to handle, particularly failures of the nodes in the system. The agents may fail in some fashion, or the network may have some bizarre behavior like asynchrony. So you have to somehow design the algorithms to behave correctly despite these 2 issues. So let's summarize the issues with false, and then we'll talk about asynchrony, and then finally the last, the open problems. So in this particular setting, the same 3 people now with the same 3 preferences, except that this second node, the red one, the communication from that node is not reliable because the node actually crashes. It fails before it broadcasts its preference to the node below, the green one. So I send the preference to him, but not to her. And I crash between these 2 steps. So if you see what happened there, the first node, the blue one, learns all 3 preferences, k, k, and t, can apply the majority, and then produce the output k. But the third one here learns only 2 preferences, doesn't know what the red node proposes. More importantly, the green node doesn't know whether the red node sent a message to the first node or not. It's a distributed system. We cannot know what's happening somewhere far away. And then the algorithm will not work now because the first guy will choose k as the output. The second one here doesn't know how to break the tie. No matter how you choose to break the tie, you can be wrong in some executions. So the solution actually might be obvious to many of you. Do one more round of communication. So in the second round, each of these 2 nodes will forward to each other what they learned in the previous round. Okay, so that's what is happening here. In the second round, if you are this node here, then you send the message to the other node saying, look, I got these 2 values in the previous round. At the end of 2 rounds now, we all have the same set of preferences. And now when we apply the majority vote to this, we get agreement. Okay, so far so good. So this is all fairly routine stuff in distributed computing. It turns out that to be able to solve this problem correctly with those validity, agreement, and termination, if you want to tolerate f crashes during the execution, so f can be 1, 2, pick a number, you must have certain minimum rounds of communication. So that adds to the delay in achieving the agreement. So the lower bound that has been proven, when I say it's well known, it's all 30 years old. Okay, it's all from the 80s. So it requires f plus 1 rounds of communication. So that was for crash failures. So crash failures are the best things that can happen to you, right? When a bad thing happens, the bad nodes stop doing anything at all. The other extreme is that the bad nodes start doing bad things to you. So crashes, when the machines crash, people complain. But believe me, that's the best thing that can happen to you. So this is the next possibility, the other extreme. You can have arbitrary behavior. And this particular failure model is called Byzantine Failures. And here is an illustration of what may happen with a Byzantine fault. So in this particular setting, the red node is faulty, has this so-called Byzantine failure. And in this first round of communication, the red node tells the green node that his preference is high, but tells the other node that his preference actually is something else. So at the end of the first round, these 2 nodes do not have consistent state, consistent image of the state at the other node, the red one. So you can imagine that this kind of failure should be hard to tolerate. I won't actually complete the algorithm here. It takes a little bit more work. But these kinds of failures have been looked at quite a bit in distributed computing literature. Actually, when I heard the talk yesterday, which was quite fascinating, Byzantine Empire was mentioned. And I was very happy to hear that because I have the same word in my slides too. It turns out that this particular choice has no historical significance at all. So this phrase, Byzantine, was introduced by Leslie Lamport, who actually received the Turing Award this year. And he will give the Turing lecture next month in Paris, rather. So here is a quote from his website, Why Byzantine? So he says that when he came up with this particular nomenclature, he knew of another problem called the Chinese generals problem. And he was thinking of these nodes of the agents as generals. And he wanted to call them something, not Chinese, because that was taken already. And so he said, I wanted to attach them a nationality that nobody will be offended by. And It turns out actually he called them first the Albanian generals, not Byzantine. But then somebody pointed out to him that maybe Albanians will eventually read the paper and might be offended, so he changed that to Byzantine. So that's the history. This is from a quote from his own website. So now if you do have Byzantine failures, you need to change the definition of consensus. It cannot be the same definition as before, because there are some bad nodes that are doing bad things. Now, you don't want your output, the agreement, to be influenced by what the bad nodes are doing. So we change the conditions accordingly. There is agreement still required, except that we cannot insist that the bad nodes agree with us. Right? We all go to Korean for dinner, and the bad node, we cannot insist that they come with us too, because they choose to do what they want. So the agreement is only required between the good guys, and we want the output to be influenced only by the inputs at the non-faulty nodes. We don't want the output, the decision, to be influenced by the inputs at the faulty nodes. And we must still terminate. So to give an example again, the same example as before. Now this time the green values are the inputs at the good nodes, and the bad node may have some input. We don't really care as far as the output goes. The output has to be in this range 1 to 6, right? Because those are the good nodes. The difficulty is that the good nodes don't come with labels saying this is good and this is bad. You don't actually know who the good guys are and who the bad guys are. You may try to infer it during the execution, but you don't have a prior knowledge on who the good nodes are. So the output has to be between 1 and 6. Again, depending on the formulation, you might insist that the output be one of those 3 values, or any value within that range. Those are 2 different problems. They're having very different computational requirements. For vectors, the same issue. You have these green values now are the inputs of the good nodes. The bad node may have some input. We don't really care. But the output has to be in that triangle again, all right, irrespective of what the faulty node does. So there is no bound on how bad the faulty node's behavior can be. But we do bound, as you'll see soon, the number of faulty nodes in the system. If you don't bound that as well, then of course nothing is solvable. So the first paper that I know of anyway that introduced this particular fault model to the context of problems like consensus is this one from 1980 by P. Shostak and Lamport. The term Byzantine was introduced a couple of years later in a paper that's called the Byzantine Generals problem. What is known, and again this is a result from the 80s, that to solve this Byzantine consensus problem, you need some minimum resources. And the resources here are number of agents and the graph that connects them. So graph here is the communication network. If I'm connected to you by a link, only then I can communicate with you. Otherwise, I cannot. If I want to talk to somebody to whom I don't have a direct link, then I must forward the messages through other people. And it's known, well known rather, that you need at least 3f plus 1 nodes, 3f plus 1 agents, super majority, not just majority, and it requires sufficiently strongly connected network, 2f plus 1 connectivity. And this is a result for undirected graph, meaning if I can send message to you, you can send to me. This is not for directed graphs. So for example, if you were to tolerate 2 failures, 2 Byzantine failures, and still solve the problem, then 6 nodes are not enough, you need 7, all right? People have been building systems like this, usually for a single fault, not more than once, just because the cost becomes too high. So that was about failures, crashes, and Byzantine. Now, the network might introduce some difficulties as well. So we are not talking about here a network that corrupts messages. That can happen too, but let's ignore that for the moment. We are talking about networks that are not synchronous, networks that are asynchronous. So basically, intuitively, all it means is that when I send you a message, I don't really know how long it will take to get there. And similarly, if I ask you a question, let's say, and you're going to send me a reply, because the delays can be very large, arbitrarily large, I cannot really bound the interval of time I should wait before I should expect a reply from you. So let's say I send you an email and I don't get a reply by tomorrow. What does it mean? This says it means nothing. Okay? You could have gone to sleep, gone away, crashed, right? That could be the case, or the messages are just delayed by a very long interval. I cannot distinguish between an agent that is crashed, that I'm communicating with, versus channel that is very slow in an asynchronous system. So you can imagine somehow this could be bad for you. So here is an example again to illustrate what can happen. So our same 3 people trying to decide where to go for dinner. So in the first round, we send the preferences to each other. So the messages from the red node are slow to reach the other nodes. So other nodes here are the blue and the green. Those guys don't get the message from the red node. Now, they have a decision to make. if you are the blue node, either you can choose to wait for the message from the red node, but then you could be waiting forever if the red node has crashed already. Or you can choose to decide where to go. Okay, so let's say we choose to decide based on what's happening so far. Then the other two nodes have to decide an output without knowing the preference from the red node. So they have just two preferences, K and T. They must pick an output. Now, they don't know what's happening at the red node. This guy is going to choose K as the majority and go there, but the other two might end up choosing T as the output, and then you have a disagreement. Is the problem clear? So this is not really a proof that you cannot solve the problem, just an example of an algorithm that does not work. But what has been known also for a long time now is that this problem actually is impossible to solve. There is no solution whatsoever if you have asynchrony and even a single crash failure. So no matter how many agents we have, even if the number of good agents is very large, one faulty agent can prevent consensus. So this is a very powerful result from the 80s as well, 1983 now, by Fisher, Lynch, and Peterson, that proves that you cannot solve consensus in the presence of asynchrony. So what does this really say about what exactly is impossible? Remember those three conditions that we had: agreement, validity, and termination. What this impossibility says is that you cannot have all three guarantees at the same time. Okay, you cannot really achieve all three properties at the same time. However, we know we need to solve this problem, right? I showed you an example earlier of this replicated data store where we want to have these replicas execute same commands in the same order. Obviously, it needs consensus. This paper says you can't do it. How are you going to build real systems? So what you do then, of course, is compromise on one of these requirements. Depending on what context you have, you make an engineering decision to say, okay, let's compromise perhaps on agreement or on termination. So different people have done different decisions. So here is one. One set of algorithms says, when bad things happen, maybe we won't terminate, right? Or it will take a long time to terminate, or we will not terminate with probability epsilon going to 0 or something like that. So termination is not guaranteed anymore, and the practical systems, in fact, do stuff like this. There is a scheme called Paxos. Again, it's a hypothetical Greek island, paper by Leslie Lamport, written in 1990, accepted in 1998. If you cannot read this bottom here, this is a note by the editor. It says that this submission was recently discovered behind a filing cabinet in the editorial office of the journal. That's not quite true, but it took them a long time to decide to accept this paper. Leslie Lamport's Turing Award actually is based, I believe, in large part on this particular result and some of the other results that he has obtained. So if you have trouble getting papers accepted within a year or two, wait 9 years. Eventually. So in any case, so that was Paxos, compromise on termination. Nobody wants to compromise on validity because that's sort of the minimum requirement you want to satisfy, but one can compromise on agreement. So agreement could be probabilistic, meaning we agree with high probability, or the agreement may be approximate, which is to say that we don't produce the exact same output, but our outputs are approximately equal. Okay, so for example, if I was doing this of Byzantine faults, then the last condition remains the same, the second condition same as before. The first condition now says that the outputs have to be equal, but only approximately equal. So if I produce the output of 3.99, you might be producing output of 4.00, and that's okay, as long as they're within the epsilon. If you're trying to decide where to meet for dinner and agreeing on a GPS coordinate, that would be just fine, because if you come within 0.01 centimeters of each other, then you are basically together, all right? So depends on the context. This may or may not be useful. So for the rest of the talk, actually, for most of the talk today, I'll just focus on the approximate version of the problem. And because the exact agreement was proven to be impossible, there is this paper from '86 that actually showed how to do approximate agreement with Byzantine faults, again from the '80s. So this is just sort of a brief history of the literature in distributed computing. There are, of course, hundreds of papers since the '80s. And still, PORC this year, which is the distributed computing conference, will have, I guarantee you, at least 1 or 2 sessions on consensus. It continues to be a popular topic. Decentralized control, completely independent line of work, often not being aware of each other, meaning that if you look at the papers from distributed computing, they don't cite the papers on distributed control. and vice versa, and yet they work on similar problems. So the earliest, if you follow the history of the literature in distributed control, the earliest paper in that line of work is by de Groot from 1974, almost exactly 40 years ago now. The title says everything. The next major milestone, at least in my view, was the PhD thesis by John Sisitlis at MIT. He's still a professor at MIT now, but his thesis is actually quite impressive. Took many steps beyond the earlier work on consensus. And then about 20 years later, there's a paper by Jad Babai and so on. That actually sort of made this problem much more popular, I think, among the community by pointing out connections between consensus and some previous results on Markov chain analysis. So we won't go there for today, but so here is the problem that they are focused on, and it will seem just the same as the one we discussed before. So-called flocking problems. You have a bunch of robots, birds, and they're all proposing a certain location to meet at or certain direction to move in. So different robots, different users, different agents propose different inputs, and the output has to be identical at all the agents. They need to move together to the same location perhaps or in the same direction. So again, the output has to be in the convex cell of all the inputs. So it's the exact same problem I defined earlier, but here the perspective is slightly different. In the distributed computing literature, the reason we are looking at approximate consensus is because we cannot solve the exact consensus problem. Whereas here, approximate agreement was, by definition, the requirement. They never defined exact agreement as the first requirement at all, because there is no real advantage in agreeing on exactly. If you have some noise in the system, you're never going to get it exactly right anyway. So the algorithms that were investigated in the control literature have this flavor, and many of you will know other algorithms like this. If you know distance vector routing, for example, it behaves like this. You have an iterative structure. There is some local state you maintain, and there's some local communication with your neighbors in the network. And after each iteration, then each agent will update its own state. And the algorithms have this property that the state of each agent remains always in the convex cell of the inputs at all the agents. If you're talking about the situation with Byzantine faults, then the state of each agent will always remain in the convex cell of the inputs at the fault-free agent. Okay, so this is something guaranteed, which what it really means is that we are carrying very little state, the minimal possible state across iterations. You don't carry things around if you don't have to, right? Whereas at the other extreme, you could remember everything you have ever learned and broadcast everything you know to all your neighbors. So those are the two extremes of the solution space. We call this thing the local algorithms. The other extreme, we can call that the global algorithm. Global simply means there is no constraint on how the algorithm behaves. So here is a very simple example of a local algorithm. Actually, I want to take a quick poll of how many of you have seen this particular algorithm. This is the consensus algorithm, iterative algorithm for that. How many of you have seen that one? Okay, good. So this is news to at least many of you. That's good. So what you see here is a network of 3 agents, and this is the agent A, B, and C, and they're connected by the network that's shown here. So A and C can talk to each other, B and C can talk to each other. And the state of the agents is also called A, B, and C, respectively. If you are an agent A, then your initial state is just your input. So if your input to the algorithm is 1, then A will be equal to 1 to begin with, and B and C accordingly, the inputs of those 2 agents. So each iteration looks like this. If you are agent A, then in each iteration, you can only talk to your neighbor C, right? And you get to update your state by this equation, the average of your current state and your neighbor's state. If you happen to be this guy, then your new state is the average of your own state and the state of your neighbors B and C. And that's really what I meant by local averaging. As an example, if the initial state was, let's say 6, 1, and 2, then after one iteration, you will get the new states as shown here. And this is just one iteration. The next iteration, you would do the exact same thing and keep doing this until hopefully something good happens. Okay, so before I proceed, here's a summary of what, like a caricature of really the 2 areas. In the distributed computing community, the emphasis has been on consensus of scalars with failures, Crash and Byzantine. with asynchrony, of course, synchronous systems as well. Typically complete graphs. There is some work on incomplete graphs, like I said earlier, 2F plus with connectivity. That's obviously for incomplete graphs. And we have looked at global and local algorithms, both. In the controls area, typically the algorithms people look at, actually every algorithm I know is local with this iterative structure. They have looked at incomplete graphs, typically synchrony or partial synchrony. Even when the papers sometimes say asynchronous, they mean something a little bit different from asynchronous than we might mean in distributed computing area. No failures, typically, and vectors. In fact, if you have no failures, the algorithm of scalars and vectors are the same. There is no difference. And there are some exceptions to the rule, but this is by and large true. So focus for the next few slides on the local algorithms. We'll go back to that example. This was the example algorithm. So if you take this equation, we can take these three equations. There are three linear equations. Can be written in the matrix form. So if you remember metrics from high school, right, the product, you take the first row here, multiply by this column, you get 1/2 A plus 1/2 C equal to A equal to 1/2 A plus 1/2 C. That's just this equation down here. If you take the second row, last row, and that column, you get this equation. So this is nothing but just rewriting of this iteration. And let's call that matrix M, then the iteration looks like that. And each iteration is simply taking the state vector multiplying by M. It turns out that if you really do that, if you run this algorithm for many iterations, eventually the state of the three agents converges to numbers that are approximately the same. Okay, now if you want them to be within 0.01 of each other, then you may run for 50 iterations. You want to be within 0.001, maybe it takes 100 iterations. But the point is that you can bring the values arbitrarily close within any epsilon you want just by running the algorithm for more iterations. Now, yeah, so we already saw this, the new state equal to M times the old state. I'm attaching a time index here. 0 means the initial value. So after one iteration, the state will be M, this matrix, the transition matrix, times the state vector. If you do one more iteration, you get M squared. And you can get the idea. If you run this long enough for k iterations, basically the new state vector, if you line up the states of three agents, will be some power of the transition matrix times the initial state. So when would this thing converge to a consensus? When this M to the K, this matrix product, looks something like this with identical rows. If the rows become identical, then of course each row multiplied by this column will be identical as well. So any matrix M for which I can assure that the matrix product matrix power has identical rows will lead to consensus. This is all rather well known at this point. But if your initial state, the states are not scalable, let's say vectors in 2 dimension, then the system may behave something like that. And what I mean by that is, let's say your initial value is 3, 4, x, y. You start here. My state might be denoted by that point, the red. I cannot point here, can I? Yeah, maybe I start here and so on. And as time elapses, we all follow these different trajectories and end up in the same place in space. Okay, this is what we mean by consensus. For scalars, something similar will happen as well. And this will work in any dimension at all, no matter what dimension vector you have. So all of these results are actually follow quite easily based on papers like this on Markov chain analysis. So if you have non-homogeneous, in this case actually homogeneous Markov chain, if you know how to analyze that, you can get to these results quite easily. We won't get into sort of the mathematical details here, but the question is, when does it work? And that's, the answer to that is quite intuitive. If we are going to arrive at the same conclusions about anything, right? If you're going to reach consensus on anything at all, we must have some common input. Our initial state, of course, is not necessarily identical, but we should be influenced by somebody in common, right? If two groups of people are influenced by different leaders, you're never going to agree on the same thing. There's no guarantee there. So what this is, at least one agent in the system must be able to influence everybody. And when I say influence, all I really mean is that there should be a path. There should be one agent who has directed path to everybody else in the system. Then you can arrive at a consensus. So for example, this guy here has a path to this fellow and has paths to the other nodes as well. And that is a minimum requirement for consensus, as you can guess, and in fact happens to be sufficient as well. On the other hand, if you have a network that looks like this, there is no shared influence, meaning that there is nobody in the system that can influence everybody. So if you take node A, the agent A, he can influence C and B, but not D, and so on. So there is no common information that we can ever obtain, and therefore there is no way to guarantee that we can arrive at a consensus. So this is the necessary and sufficient condition for solving this problem. So turns out, again, intuitively, this should be the necessary and sufficient condition under any setting at all if you want to have consensus. And there are many versions of the problem. I'm going to introduce the Byzantine one now in the next few slides. So the propagation model, by that I simply mean if you are one of the agents in the system, in each iteration your state somehow changes, your opinion changes, and that opinion is influenced by your neighbors. So what rules do you execute locally that indicates whether your neighbor's opinion will propagate to you or not? Right? Under what condition do you accept their input? Under what conditions do you ignore it? So that's what I mean by propagation model. Different models will give you different results. So here I'm going to talk about the Byzantine one, sort of tie it up to the Byzantine fault model. So the same picture as before, but let's say that this agent here is misbehaving, it's faulty, it does wrong things. This is the wolf in sheep's clothing. But anyway, this is a bad node, and the way it misbehaves is by always sending this value to this agent, which is to say that this bad node pretends that its state is always equal to this value, equal to 1. And he pretends to the other fellow that his state is always equal to 2. So I'm always giving one information to him and something else to him. And if you think about it for a few minutes, you will hopefully conclude that as the algorithm runs many, many iterations, in the limit, the state of this node will go to 1, and state of that node will go to 2. They cannot agree, because they are separated by this one faulty node, and they have no really good way to agree on things without his cooperation, but he's not cooperating. So the question then is, if this graph cannot solve the problem, what can? Okay, so we have no shared influence from a good node among all these nodes, and we need that. And so this is the question. We won't go into the details of this. I'll give you a very high level. What time is it there? 3:40? I cannot see the time. 3:05. Yeah. Okay, so which graphs can solve this problem? So this is just a high level summary of which graphs can solve the problem. Essentially, we have to make sure that there is shared influence among all the good guys. If everybody in this other room are the good people, there must be one agent who can somehow influence all of them. So what does that exactly mean in the Byzantine setting? And this is what it means. This is one way of stating the necessary condition on the underlying graph for the problem to be solvable. You can state the condition in other forms using cuts and so on. But this is intuitively what it says. Start with the communication graph that's been given to you for the entire system. Remove from that a set of nodes that may be potentially faulty. So what does potentially faulty mean? If you are trying to tolerate 2 faulty nodes, then you may remove any 2 nodes from this system altogether. Just delete them. Right? So let's say I remove these 2 nodes. Having done that, in whatever network remains now, remove any 2 incoming edges. This is a directed graph. The links could be undirected, but they could be directed too. Remove 2 more incoming links at every node that is remaining after having done the first step. What we get, let's call it the reduced graph. So this reduced graph must have somebody that can influence everybody else. So we started with a bigger network. Because we're trying to deal with bad guys, we find a subgraph of the original graph, and that subgraph has to have the property that somebody in that subgraph can influence everybody else. So this condition was there before. For any consensus algorithm, even without failures, you must have somebody who can influence everyone else. Here it says you need this even in case of Byzantine faults. So for example, if I started with a bigger network, remove 2 nodes, and remove these links from 2 links from all the remaining nodes, if I end up with this as a reduced graph, then this would be okay. This is a good reduced graph. This is acceptable. On the other hand, if I end up with this, then this is not okay because nobody here can influence everybody. So there are many, many possible reduced graphs. If you follow those 2 steps, there is no unique way to do that. There are many possible reduced graphs. For all of them, this last condition has to be true. If that's true, then we know how to solve the problem. And the solution actually is quite trivial. Here is a solution. I won't try to prove it here, but the solution is very simple. So in each iteration, you talk to your neighbors, right? So maybe there are 4 of you here who are my neighbors. I receive their state. Then I have a bunch of numbers, right? He says my value is 3, she says it's 5 and 6 and so on. I line them up, I sort them. I don't know which of them is faulty, if any, but everybody is suspect. So I throw away the outliers. I throw away the bottom F, the top F, and what remains, I do the average of those. So as an illustration, if you are this node, and those are your neighbors, and the neighbors send you these values in one particular iteration, you sort them, throw away the smallest, throw away the largest, because these two nodes are, any one of them, I'm trying to tolerate one bad node here. The smallest value may have come from somebody who's bad. I don't want to use that if it is potentially bad. And same thing for the largest value. So I throw those away, and what remains, I use that to compute by new state by averaging over them. So I end up with a state of 8 by 3 because 1 plus 3 plus 4 divided by 3. So this is one iteration at this one of these nodes. Everybody does the same thing. If you do this, this actually converges to a consensus. It satisfies agreement, termination, and validity, right? Regardless of how the faulty nodes behave. So for some reason, this particular result was unknown until recently, despite all the other results from the 80s. So actual proof itself, I'm not going to do the proof, but basically the proof relies on showing that the behavior of this algorithm can be modeled as a non-homogeneous Markov chain with good properties. And I won't get into what those properties are, but if you have the right properties, then the algorithm, if the graph has the right connectivity, you can prove that it will actually reach consensus. But we won't do the details here. So this was Scalar. Like I said, we looked at scalar inputs, complete graphs in the 80s. The incomplete result is only from 2 years ago. And this only applies to scalars. The question is, what about vectors? So vectors, as we said before, what you may be agreeing is a coordinate, a location in space where the robots want to meet. So that's a vector, 2 dimension or 3 dimension. It turns out that if you're not trying to solve a fault-tolerant version of this problem, no faulty nodes, then the network requirements are independent of the vector dimension. It doesn't matter what dimension you have, the same network conditions will solve the problem regardless of vector dimension. If you have the faults, though, then the requirements are dependent on the vector dimension. And I won't do, again, the proofs or anything like that, but just to give you a feel for what the results may look like, this here says that you require enough nodes to solve the problem, and that enough depends on the dimension of the vector. D is the dimension, F is the number of faults you want to tolerate. The bigger the dimension, more the agents you need to be able to tolerate a certain number of faults. So this is something that was not true for the failure-free case. So here is the first open problem that I promised. So for the scalar case, we know the set of graphs in which the problem is solvable tightly, meaning we know the necessary condition the graph should satisfy, and we know the sufficient condition, and those two match. Okay? For vectors, unfortunately, we don't have that. We have a condition that is necessary. We know that any network in which the problem is solvable must satisfy a certain necessary condition. And we have a sufficient condition under which we know how to solve the problem, but those two conditions do not match. And if somebody wants a nice puzzle, this is a puzzle waiting to be solved. It doesn't, I have tried this for a while, many sleepless nights. I haven't managed to solve it, but it doesn't mean it's hard. It's just that I don't know how to solve it, There are 2 more open problems coming. They're all very nice puzzles, I'll promise you that. You need no background whatsoever, I had to say in consensus, to solve the next puzzle. So the question actually is, I used to work in wireless networks before I started working on these puzzles. And in networking, you always ask the question of communication cost, right? What's the penalty I had to pay to do something, right? Or what's the capacity I can achieve for this operation, multicast or something like that. So if you think about consensus, it's a function that are computing over the inputs, and you can ask similar questions for that as well. In fact, Andrew Yao introduced the notion of communication complexity a long time ago. And so we started looking at communication complexity of this particular problem. Turns out even that was not looked at before. What is known, however, is that if you want to solve consensus among n agents in the presence of Byzantine faults, then n square messages are necessary. That's a lower bound. So of course, these messages must contain at least 1 bit. So it takes n square bits to solve the consensus minimally, even if your inputs are a single bit. What if you have a large input? You're trying to agree on a large file with million bits, a file. Then what will happen to the communication complexity? You can agree on one bit of the file at a time. So if each bit takes n square cost, then total cost will be n square L. Right? That's sort of the naive way of doing things. Question is, can you get a scaling effect given that you're agreeing on a large amount of data? And that was the question here. Turns out that you can do much better. You can do linear in the number of nodes. But without going into the details, here is a puzzle, which has been solved actually by now. But it's worth solving anyway if you want something to do on the train back to Edinburgh. So let's say there are two of us, two agents, and we both have a number, right? I have some number in my hand, you have a number in your hand. What do you want to know if these two numbers are equal? By the way, this has something to do with consensus. This is not just for the fun of it. So let's say you have a number, I have a number. We want to know if the two numbers are equal. And the question is, what's the algorithm that will check equality of the two numbers we have? There's a trivial algorithm. I'll send you my number, and you can compare the two. And if the inputs are k bits long, then the cost is k bits. Turns out that's the best you can do. If you want an algorithm that will check equality of two values, no algorithm can have communication complexity in the worst case that is less than k bits. This was shown by Yao many, many years ago for two parties. The question that was open until recently is what happens if you have more than two parties? So let's say three of us, like that, connected by three links in a triangle. We all have k bits of input. And all we want to know if these three inputs are equal. Okay, there is an obvious solution. Two of us send our inputs to the third agent, k bits each. So 2k is the communication cost. And then the third agent can compare the three values, and he will know if the three inputs are equal. You can generalize this to n parties. There are n minus one of us send input to the last guy. He can do the averaging. So the cost of that would be 2k in this case, and n minus 1k in general for n parties. Turns out that is not optimal. The optimal solution is actually n by 2 times k, half the number of agents times the length of the input. So that's the optimal solution that one can show. The way it is tied to consensus is that if you think about equality, it is like consensus in the failure-free setting. So let's say there are no bad nodes. If all of us have the same input, if we know the inputs are equal, then we choose that as our output, because that's the convex cell only contains that one input. If the inputs are not equal, then we can do something different. And so that's the connection between consensus and this problem. But for the n-party consensus, Byzantine consensus, what we're able to show is that you can achieve linear cost in number of nodes to achieve the consensus. This is still not optimal. It's within a factor of 2. And the open problem that I was alluding to earlier is to bridge that factor of 2. This is competitive but not optimal. So question again, to pose it one more time, you want to solve the Byzantine consensus problem among n nodes, n agents, optimally using the least possible communication between those agents. This is achievable, but we know it's within a factor of 2 of the lower bound, so which means one can potentially make it better. In fact, we can make it better for certain special cases, but we don't know how to do it optimally in general. Last questions for those of you who do networking. This is also open. So in distributed computing, if you look at the literature, there is a tendency to treat the network as a black box. Messages come in, messages go out. Even if you look at this particular metric here, this idea is that my metric here is a total communication that is taking place. But real networks differentiate between links. Bits sent over my cell phone could be much more expensive than bits sent over the Ethernet between two computers, right? So because capacities of links are very different, the costs are different. So we cannot just take one bit here and one bit here and interchange them. So the bits, different bits have different costs associated with it. So this metric is good if you don't know anything about the network, if the network is a black box. But in general, the network is not a black box. So here is the new sort of formulation of the problem that we defined. What we're talking about now is solving this consensus problem in a network of interconnected agents where the links have capacities, which is, of course, true in practice in a communication network. And then the question one would ask is that of throughput. Just the way if you access the website, your browser may say, you're getting 75 kbps throughput for this connection. You will have the same for multicasting. You know, you're sending data that everybody is receiving at the rate of 100 Mbps or something like that. Same question can be asked here. You have a bunch of agents that have something to agree on. How many bits can you agree on per unit time on average? given that the links in the network have capacity constraints. So it's not that I'm operating on a black box. I have networks with links with potentially very different capacities. How would I design my algorithms to take into account the link capacity? Turns out that the algorithms that are oblivious of the network and the algorithms that take into account the network characteristics are not at all like each other. So it's not like you take an existing algorithm, tweak it a little bit, and now it will perform well on the network that is given to you with link capacities. What we're able to show here, and I won't go into the details today just because of lack of time, is that we can achieve throughput that is within some constant of the capacity, meaning the best possible throughput you can get here for consensus. And then constant is 2 or 3 depending on the underlying network. So the techniques that we use here come from communications theory, coding and so on, and apply to the context of a distributed computation problem. So look, turns out that there are many, many such problems that are still open at the intersection of communications and distributed computing. Partly because the communications theorists, they tend to look at unicast and perhaps multicast. They don't typically look at other complex functions that we need to perform in distributed systems. And the distributed systems community tends to ignore the network itself because they are trying to produce general results. They don't want to produce results that are specialized for a particular network, but at the same time, the network does matter because real systems, real problems are solved on real networks. So if you look at both at the intersection, there are quite a few interesting challenges. So with that, I'm going to stop. I realize it's after 3, so I didn't want to, this is already probably too much for after lunch, but let me wrap up. So this is an area, the earliest paper that I said I know was 74 by de Groot, so 40 years of work, and yet it looks like some rather obvious to state problems are open, like the one I mentioned, vector consensus, which is an obvious generalization of scalar consensus and happens to be open. Some of the capacity questions are relatively easy questions to state and ask, but they were not asked for whatever reason. So if you are interested in these puzzles, I can talk to you later. But with that, let me thank you again for inviting me to St. Andrews.